You already
Yes,
entered?
I'm here.
Huh? Excuse me?
I'm here.
Ah, okay. Yeah. The next speaker is Dr. Zoltan Kovacs. He is an assistant professor at the Department of Measurements and Process Control, Szent István University, Hungary. The title of his presentation is Recent Applications of Aquaphotomics in the Field of Food Science. Okay, so now please start if you are ready.
Yes, can you see my screen?
I can see you.
You can see me. Oh, shouldn't be like that. Is it okay now?
Yeah, okay, I can see you.
I'm sorry, I have double screen.
The screen is okay, yeah.
All right. So thank you very much for the very kind introduction and very nice to see you. I'm very excited to be here with all of you. First of all, I would like to congratulate to Professor Chenkova for the retirement and of course for the achievements she achieved so far. And especially now I heard that you can continue working in the Aquaphotomics department. Thank you very much for the wonderful organization, especially to Jelena and Lawrence. I don't know how you do all of this because regardless of the time, you answered my emails very soon. So thanks for all of this. And especially, I don't know how you can keep everything in mind, but I think I'm in the perfect place in the program. So I don't need to talk about introduction because the previous presentations talked about the importance of aquaphotomics in the field of food science. But just very shortly, of course, we know how important the food quality is, and recently it has become more and more important because of the open market and lots of transaction of different foods. We heard many different scandals, just to mention about the apparent protein content manipulation, where infant even died due to mislabeling the products. Of course, we heard many others where falsely claimed functionality of waters were done. And also we heard a lot about incorrect origin labeling or mixing with high quality food with lower grade quality. All of these are for profits, in extra profits in most of the cases. But I think we have to aim to track them, and therefore our objectives in our faculty of food science to develop non-descriptive measurements methods for the rapid determination of food quality, develop models for the determination and quantification of some food products with high economical value, and of course Aquaphotomics has very good opportunities in this field. Here are some pictures to show what are the main food products we have been working with. And as we saw yesterday in Professor Hook's presentation, and we also saw it today, near-infrared spectroscopy has an immense evolution in the past more than half century. From room size instruments, nowadays we have smaller, more precise and more affordable instruments available for a wider and wider audience. So near-infrared spectroscopy could be a very good choice in the field of food quality assessment as well. But how it works in the conventional approach? If we take this conventional approach when we have samples with high moisture content, then we are not that happy, which is in most of the cases when we are talking about food. So in the conventional approach, we dry up the samples because water has very wide, broad absorption pattern in this region. But as soon as we remove water, then we can nicely see the characteristic peaks, for example, in this case of lactose. However, it is not practical in most of the cases, talking about biological samples and food products. And this is where the aquaphotomics approach really takes place, because in spite, when we compare the pure water spectrum with aqueous samples spectrum, then although as a first glance we don't see big differences, if we have a closer look at, for example, in this case, calculating the subtracted spectra, then we can nicely see the signal of the tested analyticum in water. So this is what is defined water mirror approach called by Professor Chenkova, where we get information from water surrounding of the different molecules in the system. And this is a very good approach because it gives a complex information about our system versus the standard analytical techniques where we can measure only single parameters and limited number of single parameters. And talking about food quality in general, in most of the cases, we cannot count the parameters which can influence the general quality of our product. So therefore, we need a holistic approach to be able to measure the quality of the samples in a fingerprint base. So this is where aquaphotomics is a very good choice, and having all the benefits of near-infrared spectroscopy and aquaphotomics, of course, it can be applied in a very wide range from fundamental research to applied research fields. And this is the second one where we mostly contributing related to food quality. Here is a picture about the very diverse applications of aquaphotomics. We have seen many approaches yesterday and today, and I think more is coming. Now in this section, we focus more in food science and food quality applications of aquaphotomics. In our team here in Budapest, we have a very wide range of tests in diverse food samples, from honey to mineral waters, not listing up everything. And as I have limited time, I will very briefly talk about these first four topics, because my students are with us today. And in the poster session, they will give more details about these research projects. So the first to mention is honey. We have a long experimentation with honey using various techniques. And of course, we put on the list nearly on the first place aquaphotomics. And Ms. Bodor will present about this poster titled Application of Aquaphotomics to detect different sugar syrup adulteration of honey. Here the aim were to determine the potential of aquaphotomics to detect and quantify adulteration of honey with different sugar syrups, and to reveal the structural changes of water as a result of the adulteration. Please visit her poster. She is in the 6th in the line today. And we also have a paper published in related field. So if for more details, feel free to check it. The second topic to mention is an interesting one, because Mr. John Luis Iniazauku originally started to work with the electronic tongue in his PhD topic, and therefore we were aiming to use this device, which is able to measure only liquid samples, for meat quality determination. And as a side project, he decided, wow, if I have meat juice, then why not to try to scan it? And then it turned out, using the first overtone range, we can very nicely discriminate the different meat products. And here actually we adulterated beef meat with pork meat in different ratio. And as he will present in his poster, we could successfully discriminate and quantify the quantity of pork meat in beef meat with the spectra of the first overtone. And the related paper was published in Sensors recently. John Luis Inez Aucu is in the 7th on the list in the poster session 1. The next topic brought from our master student, David Chandra Mugara. He started to work with mung bean. We produce mung bean juice, and our aims were to understand the possibility of rapid quality check and observation of mung beans sprouting process through NIRS and Aquaphotomics. And he applied a very interesting approach, which gave surprisingly good results. He prepared model solutions of different concentration of ascorbic acid, and we built PLSR regression. And after that, he used this regression model to predict the ascorbic acid content of the mung bean juice. And after some bias correction, we could predict very nicely the ascorbic acid content of this mung bean. Papers were published also in Sensors recently, so feel free to check it for more details. And please visit the poster session where the poster number 1 belonged to David. And recently a project of ours is the quality measurement, monitoring of different fruits, especially plums. Miss Flora Vitalis will present this poster in the poster session. Here our goal was to monitor quality change of plum during different environmental storage conditions, and also to test the applicability of near-infrared spectroscopy and aquaphotomics in early detection of Monnilia fructigena infection, which caused the brown rot in fruits. She is in the number 8 in poster session 1. And then I know everyone like spices, coffee, yogurt, and Tokai wine, but today I have to skip this as I have limited time. So I will jump to the end of the row, and in the next few minutes I'm going to talk about our research results related to tomato concentrate. In this project, the study aimed to apply NIRS and aquaphotomics to detect various forms of adulteration of tomato concentrates and to predict low concentrations of ground paprika seed, sugar, and salt in tomato concentrates. As materials and methods, we purchased authentic tomato concentrates from producers and artificially adulterated with common adulterants like ground paprika seed powder, which is a byproduct of paprika production, and also with corn starch in different concentrations. And in addition to, we added sucrose and or salt in different concentrations. In total, we produced 141 samples with different combination of these adulterants. From a near-infrared scanning point of view, we used the benchtop Metri NIR spectrophotometer produced by Professor Karl Kafka company, and we used self-developed cuvette, which was able to maintain the temperature at constant 25 degrees Celsius. We collected spectra in the spectral range between 740 nanometer and 1700 nanometer, and collected 3 consecutive spectra per each samples. For the data analysis, we used the Aquapy2 package and the first overtone range with an arsenal of different chemometric methods. Let's see the results we got. Here I'm showing the results of the classification with linear discriminant analysis, and we can say that when we were analyzing only the single adulterants, then we got very high average correct classification. In the threefold cross-validation, we got 81.3% classification of the different type of samples, and in general only the lowest adulteration level samples were misclassified. The best classification was achieved with samples containing only salt. When we included in the analysis all the other samples of multiple adulterations as well, we got again very high correct classification, which was in the validation phase about 76%, and again the low concentration samples were only misclassified. Of course, we built regression models as well for the prediction of the different adulterants and the tomato paste concentration, and in general for the adulterants we got lower than 1% average prediction cross-validation error using the first overtone range. So in conclusion, in tomato concentrate analysis, we can say that NIRS spectroscopy combined with the Aquaphotomics method was proven to be an effective technique for detecting single or multiple adulteration in tomato paste. And PLSR models predicted the adulterant concentration with high accuracy and low error. Results were presented in, published in Sensors for more details. And we have a long collaboration with Professor Chenkova and the UNOSATO team testing with mineral waters with many different objectives, and in the remaining short time I will try to capture some of these. Just to mention, our objectives were to compare the water spectral pattern of different mineral water samples to determine the applicability of NIRS and aquaphotomics in mineral water quality and analysis. And one of our main goals was to introduce a new complementary concept of water quality evaluation, and of course to see the effect of various factors such as temperature, time, humidity, etc. on water spectral pattern of different mineral waters. For this, UNOSATO team has been collecting spectra of different water samples since 2012 with this portable device, and nearly every day. And as a side, we also worked in the laboratory with the benchtop instrument to build some of our models and develop some new methods and concepts. Briefly about our results, we worked out a technique where we build based on known samples, we build up a database and check the natural variation of the good quality samples, and just simply based on the Gaussian, we can define a safety interval. And after that, when we record a spectrum of unknown quality water, then we can check if it belongs to this previously defined safety interval or not. And then the software can warn if the quality is out of the normal. But taking this with a single PCA analysis would result a too difficult picture, because even if we aim to capture only the first three principal components, then we are limited to the 3 dimensions we can visualize, and are faced to a very complex picture. But with this software, we can simplify this picture, presenting the principal components in a 1-dimensional, or actually 2-dimensional picture, taking into account the single pieces with the respective loading vectors. So if there is a change, our new sample is out of the expected range, then we can right away check what are the wavelengths contributed for this difference. This software is implemented and is in daily use, and we can see a short video how it can be even visualized. And when there is an alteration from the expected quality, then we can right away check the wavelengths which contributed to this alteration. And this has been proven in practice as well, where the software gave us a warning, and it was based on real change of quality of water. This concept was published several years ago in Atlanta. And a huge project where we have been collecting spectra, as I mentioned, since 2012, showing only 5 selected years. Here about the environmental parameters. In the first row, we see the temperature variations in daily average, showing with these box and Whisker plots. And we can see both the temperature in the first line and humidity for these 3 main waters were very similar in the presented 5 years, which gives a good rise for the comparison. We tested the effect of several factors. Here I'm showing only the temperature, and it might be a bit crowded, but I wanted to present the 6 years of analysis. And we can see we got different accuracy for the different waters. And if I summarize it in a bar chart, then we can nicely see that, for example, this first water, we got repeatedly higher correlation with the temperature compared to the others. And we did the same with the other parameters and got very nice repeatability. And just as an example to show here, for the first year of the regression vectors on temperature, we can see that some of the bands were repeatedly coming up for the different waters, but of course, some of the waters showed their unique wavelengths contributing in the regression vector. And after that, taking these coordinates, water matrix coordinates, the found wavelengths, we can see that these 3 waters show very uniform patterns, and some of them are very stable among the 6 years, and some other showed some slight differences compared to those. So in conclusion, Aquaphotomics provides a new approach in diverse fields of science, including food science, and studies have shown the applicability of aquaphotomics to detect and quantify adulteration, and in general to measure quality of various food products, to monitor the quality of mineral water. And this shows that the wide arsenal of successful applications signifies the high potential of aquaphotomics in the field of food science. Here is a picture about my team in Budapest, highlighted with red, those who will present in the poster session. And thank you very much for your kind attention. And of course, thank you very much for the collaborators and the supports from our sponsors. And I'm open for questions. Thank you very much.
Thank you very much for a very nice talk. Unfortunately, the time has already come, so we have no time to discuss. And so So if you
I'm
have
very
some
sorry.
questions or comments, please access directory Dr. Kovacs. Okay.
Thank you.
Okay, thank you very much again.
Thank you very
Yeah.
much.